All right. Again, if you want to call me, I just go by Alf. It's just easier. So what are we going to be talking today about? Today we are going to be talking about unsupervised learning, in the specific case about generative models. And for starter, we're going to be talking about autoencoders. So let's see what this stuff is. Okay? All right, so again, you have seen this stuff so many times so far. So we have here a input on the bottom part. Then we have like an affine transformation. I have here my hidden representation. And on top, I'm going to have some other item. Before we were calling the top part white hat. But in unsupervised learning, we don't have the labels. So we only have, as I was saying on the first lesson, different kind of fruits. But the teacher, she went on a strike, so she's not there. You had this poor kid trying to figure out things by its own. So what are we going to be using here? So in this case here, we are going to be trying to reconstruct our initial input. And so we have same input here, the same input here. I mean, we try to reconstruct the same input. So somehow in between, we are going to be basically perhaps learning about a efficient representation. If this guy here, the dimensionality of this one here, maybe it's smaller than this guy. So we had to somehow encode our information maybe in a smaller representation. But OK, so this is just the initial diagram.
So
yeah.
So you're saying H has dimensionalities lower than X?
Oh, potentially, yeah, it could have like a lower dimensionality than X. So you have somehow to be smart in the way you encode this guy, because you have less way of representing this guy here. And then you try to get back to the same input. We're going to say more in a few slides, don't worry.
Any example of such thing? Okay.
You're going to see soon in a few slides. All right, so equations, they are all the same, right? So we have our hidden representation, which is the affine transformation of the input, to which we apply a nonlinearity. And then we have, again, our estimation of our, again, input is going to be a affine transformation of our hidden representation to which we apply a nonlinearity. All right, so again, the input and the target, or the actually reconstruction, they both have the same dimensionality because it's the same thing. So this is why it's called autoencoder, because we are trying to encode its own input. Okay. The hidden representation is R to the D, where D is the dimension of my hidden space. The first guy here shoots in D starting from N, and the other guy shoots in N starting from D. Okay, so nothing new. So here I introduce a new kind of representation. So on the left-hand side, we have here I represent with those circles different vectors. So here is my input vector, here is my hidden vector, and here is my output vector. Whereas my lines here represent a affine transformation plus the application of the nonlinearity. In this case, instead, is a block diagram, which is more, is used more, let's say, if you're, I mean, they represent different things. In this case here, the vectors represent my vectors. Sorry, the arrows represent my vectors. So I have my input vector, my hidden representation, and my output. And this guy here represents the process of actually conversion between those different units. So in this case, the affine transformation plus the nonlinearity. All right, so dual representation, right? Arrows means something here. Arrows means something else there. But they are basically, you can use either one. This is more of a notation for neural networks. This is more of a representation for signal processing, perhaps of, when you want to apply some specific transformation to your signal. All right, so again, why would we be using this stuff here? Because labels are expensive. Someone has to get some human involved in order to label every singular example of perhaps some kind of, some object or some images. In this case here, we try to learn some kind of interesting representation without need of using these external labels. There is a paper just been released this week, I think, last week, from Facebook AI, which is not fair, but it's a very nice paper you can check about pre-training with unsupervised techniques, which is very related to this topic. So also we are going to be using these techniques whenever we have very few samples. And if you perform simply supervised learning, we are going to be ending up overfitting the dataset. So basically we're going to be learning by heart those labels without actually understanding the overall structure of your data. Instead, if we pre-train those kernels, perhaps of our convolutional neural net with an unsupervised technique, we just have those kernels being learning those structure of the data, and then we can just use a few samples in order to train our last classifier. All right, let's get more meat on the fire. So sometimes you're gonna see that weights are tied. So this guy here is called encoder, and this guy is called decoder. And sometimes you have that the weights of the encoder are equal to the decoder but transposed, right? Because you have dn and nd. So why would you use tight weights, for example, in the two blocks?
Exactly. Put in.
Say again?
Whatever you put in, you're going to get the same thing back.
But you have also a nonlinearity, right? So, but why would you use this kind of relationship? How many parameters do you have if you apply this kind of constraint? Half as less, right? So your optimization is actually going to be easier. You have less parameters to play with. All right, so let's go on.
There's probably not argument.
Huh?
There should be some other argument which uses this property, but not argument, then it should be less parameters.
Say again?
Less parameters, it's not argument. So it should be some other argument, because actually you are taking matrix which should be transposing to each other. Transposing, or how it's called, to each other. So it has some other mathematical properties.
Okay.
Which one? So why we are using this approach?
You tell me if you know.
No, I don't know. That's
Okay.
why, but argument, then we need to use this to have less parameters. It's not argument.
Okay, then it's not an argument. Let's go to the next slide. So we can choose to have different kind of losses, for example, to train this autoencoder. At the beginning, we are going to be using this kind of capital L. Oh, sorry. We use this capital L here, which is the average of all these per sample losses, where we try again to reconstruct our input with our own prediction. Sorry, this should be a hat design symbol there. If you have different kind of data, you're going to be using different kind of per sample loss. For example, if you have binary data, you'd like to use a binary cross-entropy, for example, which is the same thing we have seen in the first lesson when we were trying to classify those pixels as belonging to different spirals. That was a cross-entropy, which is the same as shown here, but for multiple classes. This is just basically the cross-entropy for two different classes. I would spend more time, but I'd like to show you some examples later. So if there are no specific questions, I just keep going for these slides here. So this input here, I'm going to be using it for binary data. For example, I have images which are black and white, so binary. Like could be like some receptors. You're going to find out, oh, I have there a data, or I don't have. Like so, there like events. No, I get an event, or there are no events. So I'm going to use this guy here, for example. Otherwise, if I have real data, which are basically, I don't know, maybe the pixels, the color of the pixel of an image, or any, I don't know, audio signals, then I'm going to use this kind of representation where I compute the square norm, sorry, the norm, the two norm of the distance of those two guys, right? The quadratic, the square of the distance between these two guys. So this is going to be basically regression, and this is going to be basically classification, right? All right. Is it clear so far? All right. Okay, so we have a loss. We have our input. So we have our input, which is going to be basically the same as our target, and here we have our output prediction. All right. So as I was saying before, here is a mixed representation between the two I showed before. Here I show with those circles inside those blocks, like the size of this specific encoder, decoder, and whatnot. Actually, no, these are actually my vectors, right? So in this case here, I have my input, for example, of dimensionality 3, and then I go up to some kind of smaller representation, and then I go back to the larger representation. And when I try here to match what I see here. So you can think about this kind of scheme as a condenser, right? So I have like a, let's say I'd like to load images on a computer faster, right? So I would like to find a smart way of compressing my image. So you can use neural network in order to compress data. And it's going to be squeezing out all the redundancy in your natural data, which, you know, it has those three specific statistics we have talked last time, over and over. So going from here to here, we squeeze out all this extra unnecessary redundant information. And then when we expand back here, we try to restore whatever we have compressed here. Yes?
So if we tried to use like a standard data compression technique, then would that be counter to our overall goal, or we're just trying to find an alternative way to do that?
That's a very good question. So if you don't use any nonlinearity here, this is becoming basically PCA, is a principal component analysis. So if you start from 3 components to 2, by training this guy here, it's going to be converging to the same result you would get by applying PCA and basically a dimensionality reduction, wherever you discard the direction on which the data has less variance, right? Do you know PCA, right?
Yeah, but even something like Huffman encoding. Right?
Yes, okay. So Huffman encoding works on a specific symbolization of your data. This one works directly with your input data, so it's going to find the best way of encoding. So Huffman encoding is expressed with binary numbers, I guess. Here you can have much better compression because you just learn from your statistics the best representation in order to squeeze out all that kind of redundancy. Yeah?
It's different from that because Huffman encoding is lossless, and the point of this is to do a lossy compression.
Not quite.
No?
So, okay, Huffman, it is lossless. I would argue that for a specific dimension of this guy is still lossless.
Well, for 3, yeah.
So you have 100%
reconstruction. So it depends on what you're using. If you're using images, you can get to compress your image with like 100% reconstruction here, because it's just exploiting that kind of unnecessary representational power that images have by, you know.
For example, if you take a PNG, so it's lossless compression of images. So it's not a JPG. PNG is a lossless compression of
The
images.
PNG is a Huffman encoding. PNG is actually zip.
What?
PNG is a Huffman encoding. It's actually zip.
Yeah, but
This reminds me more of JPEG.
I would say it's like a JPEG, but if you are like in a specific setup, you still retain all the information. Then of course, if you start reducing even more, then you start having some lossy compression. But here, the point is that you can learn directly from your input data the best way of representing the data without, you know, need of actually resorting to specific algorithms, right? All right, so this is usually what I think about when I was thinking about autoencoders. You know, something that allows me to re-encode my own input, but using a smaller, condensed representation. So I usually also think about this one as a concept vector. So if I have here different words or sentences, and I try to re-encode the same word or same sentence, this kind of, so like if you're using the one-hot encoding, maybe this representation it gives you like a more condensed concept about that one that is taking a place in that long vector. All right, so, but then there are also the overcomplete. So how does this work? So here we have a hidden state, internal state, which is larger the actual input. So you can actually say like, oh, this guy, since he has to just replicate this guy here, he can simply copy here, and then he copies it over here, right? So how come are we interested in something that is overcomplete for an autoencoder? Well, because it depends what you're actually sending here. So in here, we still have to introduce some kind of constraint, which could be, for example, we turn some of these to 0. So we have a sparsity constraint. so that each of those neurons here encode a specific characteristic of your data. Or for example, we can have like, we apply some noise here, and we try to reconstruct the initial image without the noise. So maybe we'd like to implement a denoising autoencoder, which is learning how to get rid of external noise. And therefore, it's better to use a larger representation in the middle, because by having larger dimensionality, you can, as we have seen in the first lesson, push things around in an easier way. Other things are, for example, you can use a contrastive autoencoder or a variational autoencoder, where you have basically sampling from a distribution. So all those techniques are introducing some kind of constraint over the hidden representation. Although it is larger than the input, it has somehow some constraint over just copying over the information through. Okay? And this is also very, very useful. We are going to be seeing that very soon. All right, so let's see, for example, an example with a notebook. Do we have? Yes, we have some time. So let's train our first, this guy here, a normal kind of encoding version of the, like a undercomplete autoencoder. So this stuff is on the Git repo. You're gonna have to type this one, git reset hard origin master, in order to get the latest version on your machine. I'm gonna be using the I'm gonna be using the, what is it? Autoencoder number 6. And so here I'm gonna be executing some of these lines, and here you can see we go from 28 by 28, which is 784 dimensions for representing one digit in the MNIST dataset. We are going to be going down to 30 dimensionality, okay? So this is going to be definitely a lossy compression of image. And then from 30, we are going to go back up to this large number. So I have executed that one. I get my optimizer, then I start training, and I display some results, okay? And here we have the reconstructions, I think. So these are the reconstructed images. And let me see. Image.
Before, after.
Yes, I'm showing you right now. Oh, sorry. There you go. So here you can see the before and after. So this is my input, which has been compressed down to the dimensionality, I think 30, and then we get it back up to whatever dimensionality here. So we have a very, very, very strong compression, and then of course we're going to see there is a kind of bad reconstruction. So how? But again, we managed to compress all those different pixels into a very kind of small representation, which is sort of managing somehow to reconstruct those kind of initial values. All right, so let me show you instead the denoising autoencoder, how it works. Oops. So in this case here, we assume that we have our initial input, but then again, we have the input that we observe instead. It's kind of, it's not necessarily this one, but it's like a random variable condition to our observation. So here I represent the manifold of my input data. So here, all those dots are examples of those digits. So we have said those digits are 28 by 28, which are 700 and something. And you can think about those digits as one point in this very large dimensional space, right? And here I'm showing you that all these points here, they just follow a sort of lower space, lower dimensional manifold. So those dots are not really sparsely distributed in the whole space, but they are like forming a sort of shape in this kind of space. So here we have our input x, and we are going to be corrupting our input with a specific noise. So we are, for example, adding some Gaussian noise. We are moving this input from the manifold outside to the manifold. So the task of the autoencoder is going to be just getting this guy back to the X. Okay? So the denoising autoencoder gets things that are outside the manifold and brings them down back here. So we assume that we, at the beginning, we have this guy here. We have the X, we perturb the X, and then we let the autoencoder remove that perturbation. And by performing this operation, we are going to be learning the statistics of our input manifold. So here we have a very strong assumption. We assume that we are injecting the same noise distribution we are going to be going to observe later on in reality. In this game, we can learn how to be robust to that data. So if we observe noisy input, we can just apply this denoising autoencoder in order to remove that extra noise that we have managed before to learn, right? So here we are going to be learning this kind of perturbation, and then we learn how to reverse those perturbations. So let's see how this works in the notebook. So in here, you should be scrolling a little bit up, and we are going to be changing. Instead of going through 30, we are going to 500. Yes, I understand that 500 it's still less than 784, but I would assume this is actually overcomplete because 784 are way too many dimensions in order to just to express those numbers of the MNIST dataset. So I would say that 500 is way more than what is the information content of those digits. So I'm reinitializing my autoencoder, which now has a much larger internal representation. I have my optimizer. And then here, in this cell here, I'm going to be activating this module, which is called dropout, which is dropping out some of my pixels from the input. Then here, I'm uncommenting this line here. So I have my images bed, which are basically my input images, which are getting corrupted. Here, I have my input, which is going to be image bed, which is going to be going through the model and generates the output. And then I have my loss, which is made between the output and the not corrupted input. Finally, here, I'm going to show you the image bed versus my output. So now it's training. And so basically now we are going to see whether we are able to remove that external noise, that additional noise, and basically have learned a representation. So here we have the initial digits. These are, you can see maybe a 0, a 6, a 9, and 8. And then we have these green dots, which are basically set to 0. So those guys here are set to 0, and I think the blue is -1, the yellow is +1, or something like that. So in here we have corrupted our input in this way. Has our autoencoder, the noisy autoencoder, managed to disentangle this kind of noisy layer from our digit and then remove that noise from my data? What do you think?
Yes.
Yeah. There you go, right? So you can see here, this has been really nicely restored from this initial corrupted input. So these are my inputs of my network, and the output of the network is just those very pretty images. So here we have learned how to be robust over this kind of over 50%, actually it's 50% of the pixels here have been turned to 0. And here the network managed to reconstruct half of the missing image. So this can be also used, for example, for image inpainting when there are regions of your image that are missing, for example. Or if you want to delete some part, so you have your image, you won't like to delete that photo bomber, no photo, how you call it, photo bomber, right? The guy there. So you just draw black pixels there, you send it through my denoising autoencoder.
Face come back.
Huh?
You just told us that if we will draw some pixels, algorithm will return back this 8, right? So if you will put this pixel on this face, you will pass through this one, and then this face will show up back.
No. So if you put some black pixels, it's going to try to fill up with the background. and it's going to be removing the guy who was trying to ruin your photo. So let's see. Yeah.
But the loss function x is the picture before.
Yes.
Before okay.
That was for
That's
training.
An important point. Okay.
Yes, of course. So I train with the original image, which is not perturbed, and I try to go back to the unperturbed image. But then you're just feeding noisy images, and you're gonna get cleaned up versions afterwards. All right, so I can show you some weights that has been learned, and you can see here. These haven't been basically trained, but these kernels here, they are convolutional kernels, which are tuned to resonate with some specific curvature of your drawings of your digits. So those two, may extract something, and if you have a linear combination of these guys here, you can generate those images. So let's actually check what OpenCV has, right? So OpenCV has in Paint and NS and Telea in order. So it's like Telea and Navier-Stokes in painting techniques which are there for cleaning up your data. So let's see how they work. So this one is my noise. Okay, so this is my 0.5%, 50% of the data corruption. These are my digits with corruption. These are the original digits. These are the results from my autoencoder. And these are the results from the other two techniques. Oh. Right? So right now, spending what? A few minutes, 1 minute of training, like even less, 30 seconds, we get results that are much better than state-of-the-art algorithms that big people spend so much time in creating. We just made it from scratch by just learning from data. Yeah.
And the reason that it's better is because you trained on your own data.
That's it, right? This one is only working with a specific noise we have trained, with the specific data we have used. If you apply to other techniques, it's not going to be that good. But if you can tailor your algorithm to your data statistics, then we just have to reconstruct the manifold, right? That's it. All right. How much time do I have left? My God. I have 15 minutes, I guess. All right. Let's see if I can do some more stuff. We have like much more stuff. I'm really sorry. I'm going to be running so badly. All right. So here we have the contractive autoencoder. What is this guy? So despite the very scary name, this is actually very easy to understand. So here we have again our input manifold, whereas our dots here represent the specific data points of our data set. And these ones are representing basically the surface or whatever this kind of object in this high-dimensional space where all my things are laid. All right, so I have there my input sample, and then I have this reconstruction. So what are we doing here? My reconstruction, it has a loss associated to the reconstruction term, and then there is this guy here. What is it?
Renormalization.
Hello. What is it? What is this symbol?
Oh, nabla.
Okay, nabla, sure. What does nabla do usually? Gradient of my hidden representation with respect to my input. So what does this say?
Penalize it.
Penalize what?
If the hidden representation is very far away from the input.
No.
Penalize the weights.
Large weight size.
So this one is going to be penalizing the sensitivity to the X. So basically, if this is very, very good, if this is very strong, my hidden layer is going to be completely insensitive of the input. So whatever is going to be my input, my edge is going to be always the same, right? So if this is very, very large, and if I try to minimize this loss, this means that I don't want to be sensitive to the input. Anything I send, I just put always the same constant, right?
So it is insensitive to noise in the input. So
This is insensitive to anything. It's like you're talking, I don't listen. All right. So this is like basically I don't want to listen to anything that's happening over there. So I'm like putting my right. Okay, so this doesn't work. I mean, if just this one, and this one is like somehow trying to do something, right? So this is trying to reconstruct, whereas this is trying to avoid any kind of variability of my hidden state with respect to every direction in the X. So how does it work? The first part penalizes insensitivity to the reconstruction. So in this case here, my X can move in this direction, right? So this guy here is penalizing whether this guy here is not sensitive to variation in this direction. So this basically makes this guy respond to variation in this direction here. But this guy here penalizes sensitivity to any other direction. So this one say, okay, this guy shouldn't be able to move anywhere. But this one says, okay, make it move towards this direction here. And so this is called the contractive autoencoder, where we avoid, so if we are just happening to just fall outside the manifold, that's actually bringing me back on the manifold. I go outside the manifold, that's like back to the manifold. If I am on the manifold, everything's just fine, because there is my reconstruction term, which is say, life is good. All right, so this was the contractive autoencoder. Now we're gonna be doing fancy things. Ready? I have 5 minutes now, 10 minutes, disaster. All right. Yeah, penalize and incentivize in direction, and that's just the penalized direction. All right. Cool, huh? All right, that's my basic autoencoder. So what does it do on this stuff? Here we have all those samples that we observe in the data, right? So those balls are the samples. Now, as I said before, every digit can be thought as one dot in the 700 whatever dimensionality. And this is my one image, another image, another image, another image. And this is basically the path where only possible images, not possible natural images can occur. So I have my lowercase x, which belongs to this manifold curly x, which is a subspace of Rn. So this guy is my example, and this guy is the manifold. On the other side, what do we have? So the point of using autoencoders is that, oh, how many dimensions do I need in order to represent this guy here? Although we are in 3 dimensions here, you can think, I get this one, I do that. How much do you need? Just 1 dimension, right? So that's what the autoencoder does. You just get 1 dimension, although 3 were used there in the representation. And I say, all right, so I have my Z, which is my hidden representation. It lives on this manifold here, which is under subspace of this guy here. And I get my first element here. I get the last one there, and I just do stretched, right? All right, sweet, very cool. All right, this is basically what the autoencoder does. Now, how can we go back that direction? Meaning, how can I get here a sample and then try to go on the other side? How can I choose samples? So if I would like to sample from here, like using a non-parametric sampling, so I have or to learn the distribution of those dots here, just to see where they are usually happening to be, or I have to enforce here some structure so that I know what is the structure, then I just sample from that distribution. Yeah?
What if it's not a unique function? Like, what if there are loops?
Where?
Like, in this curve here, you've drawn like a straight line, but what if it's not unique?
So I'm just showing you 3-dimensionality and 1-dimensionality. This stuff, we said is 700 dimensions, and this stuff is maybe 30 dimensions. So loops and things are taken care by the larger dimensionality.
Okay.
All right, so I really have to rush now, sorry. So autoencoder recap. So we have here the neurons, we said the affine transformation, and here we can show those as those blocks, encoder, decoder. So, variational autoencoder. Someone yesterday told me, I spent the whole last month trying to study those variational autoencoders. Wow. I mean, I even read the article. I didn't. It's too hard. I cannot understand. It's so complicated. So I'll try now to explain variational autoencoder in 1 minute. Maybe I can do a better job than, I don't know, someone else. All right, so let's start. We have, these guys are my classical autoencoder. We have an encoder here. We have a decoder over here. Variational autoencoder. We have an encoder over here and a decoder over there. Same, right? Nothing changed. Second step. Oh, Okay, I'm outputting two things here. I'm outputting some means, and then I'm outputting some distribution, some variances. These maybe are like diagonal metrics, so they are all independent. All right, so then here I just sample. So here I output these guys here, and then given that I have a mean and then I have a variance, I can sample one of those z's here and use those z to reconstruct my x. So it is like basically having here my encoder, which is ending up with those two guys here, and here I sum a noise. So I go to the representation, oh, I get some noise, I get kind of off the representation, but then my decoder tries to get me back on the manifold, right? So this one is basically, instead of adding noise to the input, so I was in the input, I get outside the input, then I go the latent space, and then I go try to go back to the input. In this case here, I add the noise to the latent representation, but then again, I try to get back to the same point where I started, okay? All right, so, and there, what did we do? Well, this one can be thought as a variational autoencoder without the variance part, right? So this is just outputting the mean. So this one gives me input, a value, and I reconstruct this guy. This guy instead, from here, I can think here, I basically manage to get a sort of distribution, and then from the distribution I do a sampling, and then I go back up there. Yeah?
You just append this B of Z to the latent representation, right?
Say again, sorry?
You're just appending these random bits to the latent representation.
So if here I have D items,
Yeah.
here I have 2D items.
Right,
I have
where
twice as
half
many.
of them are the same, are the same D from there,
Of D,
and half
yes.
of them are just random numbers.
Yes, which are expressing how much those specific characteristics are further away from that specific point. So you have, if you have D different explanator of your input, the variation, the variance, it tells you how much is the uncertainty over that specific value. So here you just have, okay, my input can be expressed with a few values. And here I tell you, oh, my input can also express by those few values, but I also tell you how certain I am over each of those four, perhaps, characteristics.
Oh, so you're saying X is larger on the left.
Both x's are the same.
Okay.
This one, let's say we start from 100 and we go to 4. But in this case here, I know how much is each of those four, how much is the uncertainty associated to each of those four characteristics. Here, you don't know how far you are in guessing the correct code. Here you have also this notion on which is telling you how certain you are about a specific feature. Really running out of time. All right, so let's see what it does. So the encoder maps from the input to the x, and we have said that this guy here is twice the dimension because we have the means and the variance. And the other guy goes from, he samples from the latent variables space, and it gets back to the to my prediction. All right, so variational autoencoder in drawings. So we start there with an initial sample. We go down here, and then from here we actually add some noise in the encoding part. So we start encoding, but then you get somehow pushed away. In here, we go back over there by sampling, and then we try to get this guy here to be very close to the initial guy, right? So potentially, if we didn't have the additional noise, we could be basically going here, but then here, every time we get new noise, so every time you get to point somewhere else. And by training this guy, you get to reduce the distance between those two guys, and you become insensitive to this guy, this noise. Something else. What we also like to do here is to be basically invariant to this kind of distribution. So we can also enforce here this guy here, which is a loss associated to the distribution that those guys here should assume. In this specific case here, I'm saying, oh, the distribution of these z's, those latent variables, should follow a normal distribution. so that I can easily sample from here, and I get meaningful examples over there. So in this way, basically, I try to remove the association between this guy here and the guy who generated it, so that I can basically have a nice distribution from which I can sample and then have a nice generative model. All right, a few slides more, because I think you're interested in this one. Are you? Sorry for not taking too many questions, but I have like 1 minute. All right, generative adversarial networks in 1 minute. Yeah, I'm sorry, seriously. But tomorrow we have more stuff coming, so or this way or this way. We have so the next notebook on the GitHub page is going to be simply running that variational autoencoder, which allows you also to do something very nice. So you're going to have 1 point here, 1 point here, and then you can just move that point from one location to the other. You're going to be seeing how interpolation in the latent space is going to be corresponding to interpolation actually in the input space. So you're going to see basically having mathematical operation performed in the latent space, in the hidden space, corresponds to basically different shapes interpolating to different images. So you can go from like your face and your girlfriend face or boyfriend face by just interpolating those latent variables corresponding, first one your face and the other one is your girlfriend face, and you're going to have very weird faces in between. All right. Not that you're weird, but you know. All right, so 1 minute, then.
1 minute or God, run.
All right, thank you. I won't run, but I don't stop me because, well, stop me later. All right, so you understood this one, right, more or less. Instead of having just the E's here, I have twice as many guys, so I have also the uncertainty associated to each of those elements. So, variational autoencoder, right? Generative adversarial networks. Actually, they are almost the same. I mean, very similar. All right, so we have similar colors. So we have a sampler here. Sampler, same sampler as here. This sampler was getting information from here. So there is some information coming from our input. Here there is no input. So this is unconditional. This guy is sort of conditioned to whatever we have seen down here. So we have a generator. Same color of the decoder. Same. Here I have my x hat. I have my x hat. I guess it's the same. So far we have same modules, right? All right. Next one, x. There. Okay. Everything the same so far. Oh, what is it? It's a switch. Discriminator. So what is this stuff? So we have a generator which is basically getting some noise and is trying to generate something cool. And here we have another X, which these two guys are not related. Then we have a discriminator here, which is just trying to say, is my input coming from real data or is my input coming from fake data? So this guy's task is to discriminate between fake input and true input. At the beginning, it's going to be very easy because this is just randomly initialized. So this guy's job is very easy. You're going to see trash here and good things here. The nice point is that this guy is going to provide me gradients through. So I can improve this guy's performance by seeing what are the actual meaningful information this guy used in order to tell me that this is fake and this is real. So this guy here, when he gets the job done of telling these two apart, is going to provide me. It's like a spy. It's going to tell me, you made a mistake. Okay, what is the mistake? That one, okay, let me fix. So this one is actually trying to fix the mistakes this guy tells it by using simply a gradient signal. And so overall, when you train this guy is going to be improving its own performance. And it's going to be converging to just produce outputs which are looking exactly the same as the data from our input distribution. So they are basically undistinguishable. And this guy here, best job is going to be just being guessing 1/2, no, 50%, which one is the real data and which one is the fake data. The point here is that we don't have any conditionality on the input. So these are just generating like very real looking data without actually having never observed real data. This guy here instead generates, real data, but it has some knowledge of whatever is in the input, and that's why we had to enforce that kind of normality, over here with that KL divergence loss. All right, one more. All right, so the generator maps from the hidden space to the input space, from Z to X hat, and the other one goes from the or X, this one, to my binary output, which is going to be or 0 or 1, like it's correct, it's like true, it's coming from the it's coming to the real data, or it's coming from the fake data. So finally, how does it work with the graphics? So first one, we have our input. Remember, in the variational autoencoder, we were starting from our input data, we were going here, and then we were going back. Here we don't have the input involved. We just start random noise. From the input, random noise, we get the generator, and we say, this is my guy here. And then we have the discriminator saying, I think it's fake. So this guy is going to tell this guy why he thinks it's fake, and this guy is going to try to improve the shooting in order to shoot on the manifold. Then also the discriminator is going to get some other input, and it's going to say, this is going to be a good value, right? So this guy is trained across with using these samples, and this guy here just tries to shoot on the manifold. And finally, the way you train this guy is just using a min-max game over this value function, which is basically one is trying to fool the other. The generator tries to fool the discriminator, and then you have just here the discriminator trying to do a good job in classifying the real data. So again, this is going to be a min-max game over this value function. I know it was a lot of stuff, but the whole point of this stuff here was to tell you that once you train this guy here, you end up with two different things. First one is going to be a very awesome generator, which goes from random noise, like a vector of 5 elements, Gaussian, like white noise, 5 elements, and that one is going to be generating absolutely gorgeous pictures of your, model, whatever you train the thing on. They really train on bad things. Okay, don't check bad things. Seriously. The other one, so this is one of the things, right? Why do you use a generative adversarial network? Generative, no? Why is generative? Because you have an absolutely amazing generator. But what do you have here too? A discriminator, right? What does it do, this one? It's absolutely super well trained in telling apart data that stays on the manifold versus data that is not on the manifold. So some of you yesterday asked me, how do I train a classifier in order to find anomaly detection? Right? This way. So you get this discriminator just learning very, very well what is your input data manifold. And therefore, if you have some outlier, it's going to catch it. It's like, it's fake data, right? So don't forget that whenever you train these guys, you don't get just the generator, which is why people mostly train these generative adversarial networks, but you get also a very, very, very nice discriminator for free, right? All right. Sorry for running so much. You have the other examples on GitHub. And I see you, I guess, tomorrow for sequence learning with recurrent neural network and LSTM. Thank you for listening.